Okay, sir.
May I request all participants to switch off their camera and mute their microphones except the video.
Okay, sir. Okay. Okay, sir. We can go.
Please, you can start.
Okay, sir. Honorable Vice Chancellor Professor M.V. Alagavadi, respected Registrar Professor Basavaraj Donor, the speaker of today's evening Professor Datar, Deans of schools, heads of departments, faculty members, non-teaching staffs, students, distinguished guests and dear participants. Good evening all. We are delighted to welcome you to the D.A.E. C.V. Raman lecture hosted by the Department of Physics in association with Indian Physics Association and Board of Research in Nuclear Science. I am Sridevi from First MSc Physics, your host for this evening. The Department of Physics has hosted several events in the past to nurture young talents and to imbibe in them the art of scientific inquiry. The refresher course in experimental physics, the No Nano programs have reached many physics enthusiasts in the past. Today's event, I am hopeful, will evoke in you a keen interest in the beautiful subject of physics. The Nobel Prize is a coveted award, and the Nobel Prize in Physics is certainly a dream of every physicist. Today's speaker, Professor Datar, will speak on the Nobel Prizes awarded in the field of nuclear science, a subject which has played a role not just in physics but in medical science, electronics, and of course, the internet. With this brief introduction, I welcome you all to this program and invite Dr. Deepak Samuel, the Dean, School of Physical Science, to deliver the welcome speech.
Thank you, Sridevi. Honorable Vice Chancellor, Professor M.V. Alagavadi, today's speaker, Professor V.M.Datar, Registrar Professor Basavaraj Donor, the Controller of Examinations, Deans, Head of the Departments, faculty members, non-teaching staff, and students. The Department of Physics is very happy to host this D.A.E. C.V. Raman lecture in association with Indian Physics Association and Board of Research in Nuclear Sciences. Professor Datar is one of the prominent figures in the upcoming India-based Neutron Observatory project. As you may know, INO is a 2,000 crore mega science project of our nation, and I am privileged to have worked for some time under his leadership and to have been a student in some of the lectures he gave while at the TIFR. In spite of his ability to make complex calculations on the fly, he was very approachable by the students, and his style of teaching was liked by many of the students, specifically the students of the INO GTP program. For me personally, Professor Datar has set the standards of how research has to be conducted, and I have benefited immensely from the small discussions on many interesting topics. Today, I'm very happy that Indian Physics Association has given us the opportunity to host him at CUK, and I welcome you all to this lecture on Nobel Prizes in Nuclear Sciences. Thank you.
Thank you, sir. I would like to invite our Honorable Vice Chancellor of Central University of Karnataka, Professor M.V. Alagavadi, to inaugurate the session.
Thank you. Today's speaker, Professor Datar, Deans of Schools, Heads of the Department, faculty members, and students. The growth of science is vital for the development of any nation. Science is the weapon to demolish irrationalities and illogical practices through which a civilized society evolves. India's contribution to science, specifically modern science, is substantial. More importantly, the stature of Indian scientists is worth mentioning. Satyendranath Bose, a humble lecturer in a Calcutta University, wrote to Einstein requesting him to translate a paper to German. Einstein agreed to translate the work, and the rest is history. Today, we have a class of particles named bosons, the so-called God particle, which was recently discovered in a boson. Those were the days when scientists dared to question the status quo. Bohr did not fear that his work would be disregarded in the light of the existing theory. Instead, did not consider a work from a little-known teacher to be unworthy of publication. The attitude of these scientists resonates well with our university's motto, Vidya Dadati Vinayam. Knowledge makes one humble. C.V. Raman made profound discoveries using simple optical instruments for which he won the Nobel Prize. The inspiration for all his works came from his curiosity in knowing the reasons behind the color of the Mediterranean Sea. Today, Raman spectroscopy is an established tool in many scientific fields. A scientist finds his motivation from the motion of the planets, the stars, the colors of the sky. No motivation can be bigger than that coming from the nature itself. Nobel Prize Physics for the year 2020 was awarded to three scientists for the work in black hole formation, and perhaps we may be dismayed by the fact that none of them were Indians. But it is pity that very few of us know that the entirety of the work is based on a mathematical description of black holes given way back in 1950 by a lecturer from City College in Kolkata, Professor Rai Chaudhary. My dear colleagues and students, the history of our science and our scientists, while making us proud, should also make us motivated to take those small steps that are required for a bigger tomorrow. Today's speaker, Professor Datar, was the project director of our nation's mega science project, India-based Neutrino Observatory. I am very happy and proud that Central University of Karnataka is a collaborator in this 2000 crore project. And I thank Professor Datar for supporting our students in their project work at IICHEP Madurai. I am happy to note that many students from the Department of Physics trained at this center have been immediately absorbed for PhD programs abroad, including at places like CERN, GSI, and JLab. I am sure he knows the problems of setting up a science laboratory on par with international laboratories. At the same time, I am sure he will tell us the pleasure of doing science through his experience in working in both international and international laboratories. I once again welcome you all to this program and look forward to hearing his interesting lecture on Nobel Prize in Nuclear Science. Thank you one and all.
Thank you, sir. Now, I would like to invite Professor Basavaraj Donor, the registrar, to give an introduction about Central University of Karnataka.
I think he's not there. So we may proceed to the next part.
Okay, sir. Now, I invite Dr. Sujasmita Saho, Assistant Professor of Physics, Central University of Karnataka, to give an introduction about D.A.E. C.V. Raman lectures.
Thank you, Sridevi. Good afternoon, everyone. Honorable Vice Chancellor, Professor M.V. Algardi sir, respected Dean Dr. Deepak Samuel sir, esteemed speaker, Professor V.M.Datar sir, all the faculty members, and my dear students. I feel privileged to introduce about and speak about the D.A.E. C.V. Raman lecture. This lecture series was initiated in the year 1989 by Indian Physics Association with a grant from the Department of Atomic Energy. Initially, the lectures were delivered for undergraduate students in science and professional colleges within the limit of Greater Bombay on topic in nuclear science and their applications or other topics of interest to the Department of Atomic Energy with the objective of exciting the young minds. Since the year 2009, the D.A.E. C.V. Raman lectures have been extended to all parts of the country and delivered by distinguished scientists from nearby institutions. The selection of the 4 D.A.E. CV-RAMAN lectures per year for deliver one lecture is made by the Executive Committee of Indian Physics Association. Since the year 2017, the number of speakers has been increased to 5, out of which one would be a woman scientist. The D.A.E. CV-RAMAN lecture continued to be supported by the Board of Research in Nuclear Science. The Indian Physics Association has been an active platform for physics community in India for past 50 years and has constantly facilitated interaction through many different channels. The pandemic has opened up new opportunity of networking through online interactions, and Indian Physics Association has utilized this opportunity very well. The IPA 50 webinar series started in September 2020 is an example of the same. The Indian Physics Association plans to initiate new programs to attract and engage the young researchers. The Lighting with Physics Society of other nations will be actively pursued to enhance interactions of Indian physicists within the global community. Let me take this opportunity to request students and faculty members to apply for membership to the Indian Physics Association and support them in their scientific endeavor. Thank you. Over to you, Sridevi.
Thank you, ma'am. To introduce our speaker, may I now invite Dr. Bharat Kumar, Assistant Professor of Physics, to this session.
Thank you, Mr. Devi. First of all, I would like to thank the organizers for giving me this opportunity to introduce our today's speaker, Professor V.K.Datar. We all know about Professor V.K.Datar's contribution, but since I have been given the responsibility of introducing him, let me recall everything, whatever we know about him. So Professor Datar was a project director for India-based Neutrino Observatory since 2016 until recently in 2020. And he was a senior professor at the Tata Institute of Fundamental Research, TIFR, Mumbai, during May 2015 to May 2020. He actually obtained his PhD from the University of Mumbai in 1983 and did postdoctoral work at IPN Orsay, France, and SUNY, USA. Before moving to TIFR, he was a distinguished scientist and head of nuclear physics division at Baba Atomic Research Center during 1975 to 2015. He was a senior professor of the Homi Bhabha National Institute and Dean Academic for Physical and Mathematical Sciences at BARC. He has also been an adjunct professor at the School of Natural Sciences, TIFR. He joined the Nuclear Physics Division, BARC, in 1975 after a year at the BARC Training School. His areas of interest include low energy nuclear physics, tests for conservation laws, and symmetries and neutrino physics. Some of his recent works include an accurate measurement within 10% of the tiny radioactive decay of the order of 10 to the power of -7 from 4 plus to 2 plus resonance in 8 beryllium, showing collective enhancement characteristic of a dumbbell-shaped rotor. He has also worked on melting of shell effects on the nuclear level density in the doubly closed 208 lead region using a novel transfer fusion method in conjunction with neutron TOF measurements. And he has worked on estimating the sensitivity of ICAL at INO for primordial magnetic monopoles and anomalous KGF-like events. He has worked on performance of compact muon veto detector with a 99.98% efficiency, simulation of pion-induced neutral particle background for shallow depth ICAL with a 99.99% efficiency charged particle veto detector. So he was also working on possible use of large deuterated liquid scintillator for supernova neutrinos. In the past, he has searched for and ruled out an improved at an improved level of sensitivity during that time the electric charge non-conserving beta decay. The standard axion through its 2-photon decay at the Tarapur nuclear power reactor using the thermal neutron capture by protons. The 17 kilo electron volt neutrino mixing in 35 sulfur beta decay, and also on long range nuclear forces of van der Waals type. With this, I will thank the organizers once again for giving me this opportunity to introduce our today's speaker. Over to you, Mr. Vivek. Thank you.
Thank you, sir. This is the moment we awaited for. We are extremely honored to welcome Professor V.M.Datar to deliver the lecture. The session is all yours, sir. May I request you all accept the speaker to turn off their microphones, and we will have a question and answer session at the end of the lecture. Please ask your questions in the comment box.
Let me try to share my slides. One minute. Oops. Somehow I have missed this. Yeah. Share screen. Share screen. Slideshow from the beginning. Okay. Can you see the slides, please?
Yes. Yeah.
And can you hear me also reasonably clearly?
Yeah.
Okay. So let me first of all thank the organizers, both the Central University of Karnataka and the IPA, and of course the BRNS D.A.E, and in particular the Vice Chancellor of the university, the registrar, the faculty members, and of course Deepak Samuel, whom I have known for quite a few years now. Today's talk is on, it's a kind of historical talk. Nobel Prizes in nuclear science. It originated on a request by our chairman, present chairman, to basically give a talk to the engineers to tell them what is the basis for the nuclear reactors developments that are going on in the country. So that's how it started about a couple of years, 2-3 years ago. So let me go to the next slide, which shows the plan of the talk. I should, of course, acknowledge that this material for this talk has been taken from many, many sources, including Wikipedia, the journals, even the original articles which came in philosophical magazine, Nature, and so on, proceedings of Royal Society, and some colleagues of mine. Okay, so I will go through the discovery of radioactivity, then the nucleus, neutron, then artificial radioactivity using alpha sources in the early days, and then accelerators, then come to nuclear force, nuclear structure, and how the nucleus provides a lab for testing symmetries. Another very important application of nuclear physics is in the nucleosynthesis that takes place in the cosmos, including our sun, which is our closest star. And finally, to make all this possible, of course, we have particle detectors, which enable us to literally see at what is happening in nuclear reactions and nuclear decays and so on. And then the fallout of some of this work in applications of nuclear techniques. Okay. So let me start from the discovery of radioactivity. So the Nobel Prize in 1903 went to 3 individuals, Henry Becquerel, Pierre and Marie Curie, and for their researches in discovery of spontaneous radioactivity in the case of Becquerel, and researches on the radiation phenomena which was discovered by Becquerel and elaboration of that. That basically this radioactivity is an atomic phenomenon. There's an interesting story here in that only 2 people were considered for this Nobel Prize by the Nobel Committee, Henry Becquerel and Pierre Curie. In those days, women were considered to be not really up to it. And although the program of radioactivity was actually initiated by Marie Curie, somehow the Nobel Committee only considered Henry Becquerel and Pierre Curie. Pierre Curie got wind of it through a mathematician friend of his who knew what was going on in the Nobel Committee. And when he came to know that only these 2 names are being considered, he wrote a very strong letter to the Nobel Committee. And we said that, either Marie Curie's name has to be there, or then, I should not be there at all. So only of these 2 possibilities. So then, of course, the Nobel Committee stepped down, and then they said that, okay, Marie Curie is in. Marie Curie was remarkable for another thing. She also got the chemistry Nobel Prize, and she's only the only scientist who has got the Nobel Prize in both physics and chemistry. And the 1911 Nobel Prize for chemistry went for her discoveries of radium and polonium, which she isolated with after a huge amount of work, literally needle from a haystack kind of work. In all these slides, or not in all, but at least in most of the slides, there are the discovery papers given at the bottom. And of course, I have already shared this with Deepak. So in case somebody is interested, you can look up this talk and then the references therein. Okay, the word radioactivity was coined by the Curies. They also found that thorium was radioactive. So they discovered the radioactivity of thorium. And as I said already, Marie Curie was already on to investigating radioactivity when she came to know that this was a peculiar phenomenon had been discovered by Becquerel. And he actually joined her in the research. So it was not the other way around. It was not that Marie Curie joined Pierre Curie. It was that Pierre Curie was doing condensed matter, research, and then he got interested in her research and joined her. So he was in some way maybe a junior partner in this piece of research, and that is why he in fact wrote to the Nobel Committee that if at all only Marie Curie should get it, not him. But if you want to give it, then it has to be her first. So anyway, they isolated polonium in July 1898 and radium. And the radium, you can just see the amount of the small amount of radium that they isolated. 100 milligrams of the stuff from about 10 tons of ore in 1902. So they actually had cauldrons in the basement of their laboratory. At that time they had very poor funding. They had to basically spend money on their own. And they did a fantastic job of taking pitch blende and separating it only, as I said, 100 milligrams from this 10-ton ore. Fantastically difficult work. Of course, they had to also pay a price for it because the amount of radioactivity that they were exposed to later led to the death of Marie Curie due to cancer. They pioneered radiotherapy. They realized that alpha particles can kill a tumor. And in fact, the first experiments on this was done by Pierre Curie, who exposed increasingly strong sources of alpha particles on his hand, and then found that beyond some activity, then there is a reaction on the skin. And then he said, okay, at least you have to stay safe below this kind of level of activity of the radioactive source. Of course, in the early days, the standard of radioactivity was the Curie, which is about 3.7 10 to the 10 decays per second. But later, of course, now it has gone to Becquerel, which is 1 decay per second. Marie Curie was very generous with the alpha sources that she made of radium, and she provided many of her colleagues who sometimes even competed in terms of research with her, like Rutherford, Meitner, Hahn, and so on, Fermi. So many of these researchers were provided alpha sources by her very, very generously. There is a very strong human side to her. She actually supported the education of her sister, who became a doctor. I think she became a doctor in Paris. And then after that, she got a scholarship. At that time, she was earning taking care of a young child in a family somewhere in the interior of Poland. But then when she got an opportunity to go to France with a scholarship, she studied there and then returned that scholarship to the Polish government in order that this help some other student. This always brings up a lump in my throat. She gave much of her Nobel Prize money to friends, families, students, and research associates. She didn't keep very much for herself. She interestingly did not patent the radium isolation process. This is just like our J.C. Bose, who also didn't patent the creation and detection of radio waves. She insisted that monetary gifts, which were given to her on various occasions, be given to scientific institutions, not to her. She assisted, the frontline doctors during World War I by taking mobile X-ray units. In fact, in this effort, she was also assisted by her very young daughter, Irene Curie, who later won a Nobel Prize herself, so that this X-raying of wounded soldiers could assist surgeons in doing the right kind of surgery at the right place. She also founded the Radium Institute, which she had great trouble in getting through. I mean, she didn't get any government support initially, and fortunately, Louis Pasteur, who is of pasteurization fame, and he developed some of these. I mean, he did his work in medicine and so on. So he helped her because he had funds, and he helped set up the Radium Institute. Of course, later the government came in and helped her. Einstein has a very interesting statement about her. She was probably the only person, sorry, who could not be corrupted by fame. Extremely down to earth and very simple living, right up to the end. Okay, then we come to the founder of nuclear physics, namely Ernest Rutherford. He was awarded the prize in chemistry, interestingly, in 1908 for his investigations into disintegration of elements and the chemistry of radioactive substances. He was nominated 20 times in physics, only 3 times in chemistry, and in fact, the second year that he was nominated in chemistry, he got the Nobel Prize. He was awarded the Nobel Prize. It is ironic that he was awarded the Nobel Prize in chemistry because he used to make, derisive statements like chemistry is just stamp collection and so on. But then finally, he got the Nobel Prize in chemistry. Apart from, of course, doing a lot of work in radioactivity and clarifying things, which was extremely important in the early days, his other important works in physics was to formulate the radioactive decay law in the same year that he actually discovered that the atom consisted of a compact nucleus, about 10,000 times smaller than the size of the atom, within the and then this was through an alpha scattering experiment, again in the same year, 1911. And what is shown here on the right, I don't know if you can see this. Let me see if I can have the laser pointer. See pointer options, laser pointer. Yeah. Okay. So you can see that the experimental measurement which he initiated and which Geiger and Muller carried out in his laboratory, the Cavendish laboratory, showed that there was too much of large angle scattering. And if the positive charge had been distributed uniformly over a volume, let's say 10 or 100 times what we know today, then the cross section would have fallen like this. Okay, it would have fallen much faster than what was experimentally found. So the fact that there was too much of large angle scattering indicated that there were extremely strong electric fields that did it, and that pointed to a very compact object at the center of the atom. Interestingly, he also proposed that in order to compensate for proton-proton repulsion, repulsion between like charged particles, there should also be a neutral particle, which he called the neutron, actually. He said the only other alternative is to have nuclear electrons, negatively charged particles, so as to keep them together. However, he didn't pursue this idea of a neutron. I think he made this proposal sometime in 1920. But this was taken up later by his student, James Chadwick, and we'll come to that in subsequent slides. The radioactive decay law, all of you know, it's that if you have n number of atoms to start with, n0 atoms to start with, then the way the time evolution of an ensemble of atoms or nuclei goes is like e to the minus lambda t, where lambda is the disintegration constant, and 1 by lambda is the lifetime of the nucleus involved. And you can also define a half-life when after every half-life, roughly half the number of atoms survive. And that is related to the lifetime, of course. So they found this law in about 1911 when they were investigating radioactivity and products of radioactivity. So for instance, one of the things that they measured was if the parent decays like this, the product which is formed that is exact mirror of this, and it grows in an exponential manner. And this has been used to date substances, including date rocks. In fact, Rutherford did the first dating of some old rocks to show that the Earth was at least 1 billion years old. And that went against the then held dogma that the sun cannot be more than 30,000 years old, or sorry, 30 million years old. So this was way beyond that. But also a more recent example is that of carbon-14 dating, where you use the exponential law, decay law, to figure out how old is a carbonaceous sample. And this works, for instance, because the carbon-14 half-life is about 4,500 years. So you can date archaeological items which contain carbon, wood, and organic things which are found in archaeological sites to about 50,000 years. But many of you may not know that there is something called the Kalfin theorem, which was, the paper came out in 1968 in Physics Letters. He had actually published this earlier in Russian journals, but Russian journals were not read very often in Western circles. So he published this paper in Physics Letters. The theorem on very general grounds shows that any quantum mechanical system with positive energy and so on has a decay rate which is exactly zero at t equal to 0. Now, of course, the theorem doesn't specify on what time scale the radioactive decay law comes into play. But this was used, for instance, by a paper by Fleming to try to understand why we do not see proton decay. In the 70s and 80s, there were many experiments. In fact, there are experiments even proposed now, the hyperchemical detector and so on, to look for proton decay on time scales of the order of with half-lives for the proton of the order of 10 to the 33, 10 to the 34 years. With a paper by Fleming in 83 pointed out that in view of the Kalfin theorem, who knows what is the time scale when the radioactive decay law kicks in? And it is possible that on a time scale of the lifetime of the universe, which is 10 to the 10 years, and because this is much, much smaller than the proton decay lifetime, which was expected at one time to be of the order of 10 to the 29, 30 years and so on, that this is a ratio which is 10 to the minus 20. The observation time by the lifetime is of the order of 10 to the minus 20. And who knows if this decay law is valid. So there is an experiment, of course, there's a couple of experiments which were done by Norman in 88 and then later improved in 1995, which showed that the exponential decay law is valid in this range of 10 to the minus 10 times t half and 45 times t half. On the higher time scale, it is supposed to be a power law, but we haven't found any evidence for that. And on the shorter time scale, it has been shown to be 10 to the minus 10. But this is way, way higher than the 10 to the minus 20 or 10 to the minus 22 required for the proton decay case. So this subject is still open. Of course, you might have heard of the so-called quantum Zeno effect. E.C.G. Sudarshan, an Indian origin scientist who died a few years back, showed that if you observe a decaying system from time to time sufficiently fast, then that state will not be observed to decay. That's the quantum Zeno effect. And this has been experimentally observed by Dunn. So these are the connections with the radioactive decay law that I thought might be interesting to students and faculty. Okay, now I come to the discovery of isotopes. So nucleus with a certain number of protons can also have differing numbers of neutrons in them. Okay, of course, we haven't yet come to the neutron discovery, but already in, sorry, there is some background. Is it due to my background? Okay, stop. So, for instance, Frederick Soddy got a Nobel Prize in chemistry for his contributions to chemistry of radioactive substances. You can actually separate out the radioactive decay products and then also throw light on the nature of isotopes which are thus produced. Aston, of course, for his discovery of, for discoveries using the mass spectrograph of isotopes. That is, if you let's say you have chlorine, then you get 2 isotopes. If you have tin, for instance, you have something like 10 isotopes. So he showed that there are 10 lines, and the intensities or the areas under those curves which you get in a mass spectrogram are related to the abundance of that element in the naturally occurring substance. Harold Urey, of course, got his Nobel Prize for the discovery of heavy hydrogen. He also worked on the enrichment subsequently in the Manhattan days on the enrichment of D2O, U-235 enrichment, and so on. And also he did some very pioneer work in other areas, like how can you produce the first molecules that are responsible for life, and so on. Okay, so the present picture of the atom, again, I will come to the neutron a little later, but the present picture of the atom is that you have a nucleus at the center and you have electrons orbiting it. The nucleus is about 10,000 times smaller than the size of the atom. And of course, now we even know how the charge is distributed in the nucleus. And this is through the pioneering studies of Robert Hofstadter. who got the Nobel Prize in '61 for actually doing electron scattering experiments, which told us about the charge distribution, the charge distribution in a nucleus, and also which led to the fact that the radii of nuclei go like some constant R0 times a to the 1/3. This came out from his studies. Of course, these were corroborated later also by hadron scattering experiments, which essentially gave a similar result. But the hadrons in general, protons, neutrons, and pions, and so on, they interact with through the strong interaction. So they give you an idea of both the proton and neutron distribution, whereas electron scattering gives you only information about electric charge. Of course, if you do very specific studies like backscattering of electrons, then you can get the magnetic moment distribution as well in nuclei. That same year in '61, of course, Rudolf Bohr was one of the youngest researchers to get a Nobel Prize for his discovery, which now bears his name, the Bohr effect, the recoilless emission and absorption of radiation in crystalline environments. So he did this during his work towards his PhD. So this is an inspiration for all PhD students. In fact, if you're lucky, you might even get to a Nobel Prize. Okay, the scattering experiments of Hofstadter were taken a step further down the size axis by experiments for which Friedman, Kendall, and Taylor got the Nobel Prize in 1990. So the experiments which actually showed that the nucleus is a very compact object inside an atom. Similar experiments which look at basically deep inelastic scattering of electrons and protons, and also unbound neutrons, as deuterium and so on. They found evidence for point-like objects inside the proton. So if you go to high enough energies of electrons, then the de Broglie wavelength, as you all know, shrinks in size, and in the relativistic domain, it just goes like 1/e. So if you are sufficiently high energy at, let's say, a few GeV or 10 GeV and so on, then you can look for this deep inelastic scattering, and it shows exactly the same behavior. You have too much of large angle scattering, which points to point particles which are scattering the electrons. And in fact, Feynman, who was himself a Nobel laureate winner for his work on quantum electrodynamics, helped in the interpretation of some of these deep inelastic results in Stanford and MIT. And he had, of course, initially called them partons, but later then these partons were identified as quarks, which were proposed by Murray Gell-Mann, fractionally charged objects inside a nucleon, point particles inside the nucleon. Okay, so now I come to the discovery of the neutron. So as I said already, there were suggestions by Rutherford of a neutral particle inside a nucleus, so as to hold the nucleus together and help it overcome the Coulomb repulsion between protons. But James Chadwick actually made this discovery in 1932 in experiments, very simple experiments, but very clear-cut experiments that he did. So there was some problem that was identified by in the experiments of both Becker and Irene Curie, and then later Irene and Joliot-Curie in 1932, who found a very penetrating radiation. And they thought at that time that they were extremely high energy gamma rays. But Chadwick settled this issue by using an ionization chamber and a cloud chamber picture. He had by that time a very able person in his lab who, I think the name was Elliott, who could actually run the cloud chamber and ionization chambers with great success. And he actually took pictures of proton recoils. And from the the angular distribution of these proton recoils, he could figure out that the mass of the neutron was roughly the same as the mass of the proton. So that basically set the stage for understanding the nucleus in terms of n protons and z protons and n neutrons. And this is the article, the discovery article in Nature, 1932. Now we go to artificial radioactivity, fission using sources, and finally accelerators, which are extremely powerful devices in all modern day nuclear and particle physics. So the first synthesis of a new radioactive element was done by Frédéric Joliot and Irene Joliot-Curie. Irene was the daughter of Marie Curie, And they got the Chemistry Nobel Prize in 1935 in recognition of this synthesis of new radioactive elements using sources. Later on, Frederick Joliot was responsible for setting up the Atomic Energy Commission in France, which is called the CER, and the CNRS was instituted by Irene Joliot-Curie. So the first institute was the Institut de Physique Nucléaire in Paris, in Orsay, near Paris, on the outskirts of Paris. Just as charged particles can be used to synthesize new elements, make reactions, of course, you can use neutrons, and neutrons have the great advantage, and they were, as I said, already discovered in 1932. Enrico Fermi used them to great effect to see if you can make new radioactive elements. So he took a whole series of elements, right from the proton to uranium, and tried to see what are the new radioactivities that you can produce. Because neutron doesn't face the same Coulomb barrier as a charged particle, like the alpha particle. So it can merrily go into a nucleus and make a reaction there. You can have a capture reaction, you can have an alpha reaction and whatnot, and then you can make new elements. So he used this to great effect. He, in fact, probably discovered fission, and most people believe that, he misidentified the fission products as new elements beyond uranium and so on. But in any case, he pioneered the use of the neutron to make new radioactive elements. And he, of course, did many, many other things for which he is very well known. And there are two excellent biographies of Enrico Fermi by Gino Segre, the son of Emilio Segre, and The Last Man Who Knew Everything by Schwartz. I think he is also a son of a Nobel laureate, Schwartz. So I should say a few things about Fermi because he's absolutely a giant in nuclear and particle physics, astrophysics, and so on. He has innumerable contributions. So some of his contributions are listed here. He's probably the only physicist who had great contributions in theoretical physics as well as in experimental science. So, for instance, the Fermi-Dirac statistics is something which he had a great contribution to. Quantum transitions, we all know about Fermi's golden rules. He wrote down the first quantum field theory for beta decay. In fact, that paper was rejected by Nature, to which he had sent this paper as being too speculative, and Nature forever regrets it. He sent it off then to an Italian journal, a very matter-of-fact kind of person. He just sent it off to an Italian journal where it was accepted and published. He also had the first theory for the origin of energetic cosmic rays. In fact, there are two mechanisms attributed to him. Mechanism one, Fermi mechanism 1 and 2. And both are, in fact, do take place in nature, do contribute to increasing the energy of cosmic particles, which we all see as showering down on the Earth and other places. Fermi's contribution to experimental science is, of course, no less. He, of course, got the Nobel Prize for transmuting elements using neutrons. He performed, he basically got going the first self-sustained and controlled fission chain reaction in the so-called PILE project in Chicago, using just slide rule for calculations. One can't imagine these things to be done in these days, what with safety regulations and so on. Of course, he was very much a very important figure in the Manhattan Project, which made the first bomb, which was to basically preempt the effort, which they didn't know at that time how advanced Hitler was, but to do it before Hitler got to making a bomb. And then after the war was over, he just plunged into the field of nuclear resonances. And it was a very complicated and messy affair, but he just was a very practical person. He said, okay, if there are nuclear resonances, if there are too many of them, if there, we just have to, measure their properties. So using the synchrocyclotron that existed in Chicago, he just plunged into this area. Okay, now I come to another discovery which actually changed the face or the way science was done post-war. And that discovery, of course, was due to many people. For instance, Meitner actually started this program of post-uranium elements, and Hahn and Strassman were the chemists. Hahn was, of course, was a very, very elegant and competent chemist in Berlin, in the University of Berlin. But of course, Meitner was the senior person there. She was the senior physicist there. So they were looking at what happens when you bombard uranium with neutrons. And unfortunately, Meitner had to leave Germany in about towards the end of 1938 because she somehow wanted to believe that things will become better. Hitler was already taking Jews and putting them in concentration camps, but she somehow thought that maybe this will end, this madness will end. But at some point, Hahn persuaded her that you might go into one of these concentration camps, so it is better that you leave. He gave a diamond to her, his own diamond. Which he had on his ring. He gave it to her so that she would have a smooth passage across the German border to Holland. And of course, fortunately, she didn't have to use it. But in any case, she went to Holland without anything, literally. Just one day, she left Germany and then moved on from there to Sweden, where Bohr, made great efforts to get her a position in Stockholm. However, Hahn was always in correspondence with Meitner, and he reported a very interesting finding that he's finding krypton and barium in the products when you irradiate uranium. And so Frisch and Meitner, was visiting Meitner about for a week or 2 weeks in Stockholm, and they discussed this letter of Hahn, and Meitner immediately figured out, because she was the nuclear physicist, she knew the binding energy curve, and she said, yeah, then this must be fissioning. And it was such a huge step at that time, because with just a tickling of a thermal neutron, how can you cause a nucleus as heavy as uranium to just completely break apart? So they wrote this article in Nature. They sent it off to Nature, which was published in January 1939. And Frisch went back to Oxford, I think it was, and even measured the fission fragments in a detector. And in by February 39, he had a paper sent out again to Nature to report his results. Very quickly, to start with, in February and later in September, when the big paper came out of Niels Bohr and John Wheeler on fission. And this is a famous remark attributed to Niels Bohr, which is there in a book by C.P. Snow. Oh, what idiots we have all been, referring to the interpretation of the results of Hahn by Meitner and Frisch. This is just as it must be. So anyway, this is Lise Meitner, as I said, she had a key role to play in the discovery of fission, because she initiated this transuranium research when she, with Otto Hahn in 1935. She was nominated for the Nobel Prize in Chemistry 19 times between 24 and 48. And, all who's who kind of in science, in both chemistry and physics, actually nominated her. Goldschmidt, Planck, Bohr, even Einstein. And in physics, again, 29 times between 37 and 65. Incidentally, she also discovered protoactinium. So she could have been given a Nobel Prize for that discovery as well in chemistry, but also for the discovery of fission. She has done many other discoveries, like I think internal conversion and so on, many such things. Unfortunately, she did not get the Nobel Prize. And the Nobel Prize for fission, in fact, went to Hahn. And of course, she never said anything. She always praised Hahn for his work in this area. But she did have some regret on this, that she did not quite, the Nobel Committee didn't quite understand the import of this. So she did make some statement, but she never regretted that Hahn got the Nobel Prize. There is a statement in a biography of Lise Meitner by Ruth Lewin-Syme. It appears that Lise Meitner did not share the 1944 Nobel Prize. Hahn got the Nobel Prize for discovery of fission in 1944 because the structure of the Nobel committees was ill-suited to assess interdisciplinary work, because she was doing physics and interacting with the chemists. So, radioactivity which was separated out was measured by her and so on. So this may well be summarized as a mixture of disciplinary bias, political obtuseness, ignorance, and haste. But I think there is also an element of bias towards women, which is which was there in those days. Okay, so immediately after fission was discovered, people realized that you should look at because uranium is a neutron-rich nucleus, and the products are not, the stable isotopes are not so neutron-rich. So it is quite possible that you have neutron emission in fission. And indeed, this was found. And immediately thereafter, there were patents filed. For instance, Joliot in France, von Halbach, and another person who I can't read the name of, Kowalski, in 39 showed that you can actually multiply neutrons in a uranium, because if you emit more than one neutron, then that extra piece beyond one can go into multiplying the neutrons and so on. Okay, so they have filed patents for power production for the atomic bomb. Szilard had proposed a chain reaction, but not using fission, using charged particles in 33. And he had filed also a patent. He had proposed this chain reaction, but filed for a patent in 34. He tried to create a chain reaction using beryllium, where through alpha N reaction you produce neutrons, and also in indium. Landau, of course, also had this idea that you could have a chain reaction if since the neutron doesn't have charge, and if you have a process which can produce more than one neutron, then you can have a chain reaction. Of course, Szilard was responsible for persuading Einstein to write a letter to Roosevelt in 39, which ultimately led to the Manhattan Project, the so-called bomb project. I've already alluded to this building of the first atomic reactor by Fermi in Chicago. Oops, somehow I'm not able to, yeah. I hope that's right. This is the next slide. As neutrons which are produced through alpha N reactions, radioactive sources for alphas and then producing alpha N reactions, they had a rather limited, ambit, because after all, alphas from decays only come with a maximum energy of about 8.5 to 9 MeV, and the neutrons that you produce are through secondary reactions. So you have limitations on the intensity of these neutrons, but you can't, for instance, produce deuterons, or you can't produce helium-3 nuclei from radioactive decay. So for that, you need to actually accelerate particles. And Cockroft and Walton were the pioneers in this respect. They built the first cascade generator, and the money they asked for in those days was quite substantial. So it helped that Gamow, who was the one to write down the theory for alpha decay, was visiting Cavendish laboratory, and he actually persuaded, he told Rutherford that, yeah, this is an excellent idea, because what you're doing with accelerators is just the inverse of alpha tunneling, which is necessary for you to see alpha decay. So you're doing just the reverse. You're coming in with the particles such as the alpha or a proton or a deuteron, because you have that choice when you have accelerators, to come in, tunnel through the barrier and make a nuclear reaction. So Cockroft and Walton indeed did that with a few hundred keV machine. But Ernest Lawrence, on the other side of the Atlantic, was also developing the cyclotron. He had this very nice idea that a charged particle moving in a constant magnetic field has a frequency of circulation which is independent of its energy. So you can have two Ds, for instance. You can accelerate it across the gap by applying the appropriate RF, applying the cyclotron frequency as an RF. And then this always stays in sync with the acceleration process. And then the orbit keeps expanding, and at a sufficiently large orbital radius, you can extract it by either bumps in the magnetic field or applying a high electrostatic field to extract these particles. So again, there was a lot of activity in those days. I mean, this business of acceleration was in the air, and Diderot in 1928 built the first RF linear accelerator. A Van de Graaff machine was built in 1929. And then this is how, all these machines ultimately actually were refined and then became tools for discovery. So Cockroft Walton, for instance, saw the proton-induced reaction on 7 lithium to produce 2 alphas at 125 keV. This I've already said, that the barrier for proton plus lithium is pretty high, of the order of a couple of MeV. So at this low energy, it is only through tunneling, through a quantum mechanical process, that you can actually see this reaction go through. And as I said already, this is just the reverse of alpha decay, for which Gamow had written down his theory. Lawrence, on the other hand, performed reactions with deuterons because he had access to Urie's heavy water. So he put deuterons in there, and then he could produce many activities which were not seen in the experiments of Cockroft Walton. Of course, later this became an industry, and cyclotrons were developed, and then later you got synchrotrons, synchrocyclotrons, storage rings. People built colliders, then superconducting linacs, and so on. A wide variety of tools which were used in nuclear and particle physics. So this became an essential tool, but also it had applications in condensed matter and atomic physics, and also as sources of X-rays, of sources of activities which were used in medicine and so on. So this is the early Cockroft Walton. You see one of them, whether it's Cockroft or Walton, inside a Faraday cage, so as to be safe from discharges that took place, just like you have discharges of clouds. Similarly, when the voltage went too high or some dust particle came in, that you got a discharge, and to be protected from that, they used to sit in these Faraday cages and control the experiment. This, of course, is a modern version of a Cockroft Walton. I think it's about 1 million volts, and this actually is the injector to the RIC machine, the relativistic heavy ion collider in Brookhaven. The first cyclotron that Lawrence built in 1930 could sit on the palm of a human, and it's such a small size, and it was really a string and wax affair. Somehow I have thought about it, but really done nothing. But I think it would be a nice idea to take up a project, a student project, to actually build a small machine. It should be possible to build it and produce protons of a few MeV, a couple of MeV at least. This morphed much later, 12 years later, into the largest cyclotron that was built, the 184-inch at Berkeley by Lawrence. You can see the huge size. I don't see there is a human there, but it's absolutely, 184 inches like something like 15 feet or so, about 5 meters across. Very big device as compared to this. Okay, let me see how I'm doing in time. Maybe I'm going a little slow. So the Nobel Prize in '49 was given to Hideki Yukawa for the prediction of mesons, which are the basis of a short-range nuclear force. So the short-range nuclear force goes exponentially down, e to the minus r by lambda by r, where lambda is the Compton wavelength of a meson that he predicted to have about 100 MeV to account for nuclear forces which have a range of about 1.5 Fermi or so. And Cecil Powell, in the process of discovering cosmic ray interactions with nuclei in films, photographic films and plates, he discovered evidence for a pion, which had a mass of about 140 MeV or so. And these are the papers, Okuliani, Powell, this is the discovery paper, and the Yukawa paper in Proceedings of Physical and Mathematical Society in Japan. So these discoveries led to the field of pion physics and later resonances in nuclear physics and particle physics. In a parallel way, things were happening to measure electromagnetic quantities associated with protons, neutrons, and nuclei. And Otto Stern, after a very long period where he was also nominated, I think, a record number of times, I think even more than Lise Meitner. I think he was, if I'm not mistaken, he was nominated, I think, some 70 or 80 times. And then finally he got his Nobel Prize for discovering the molecular ray method to measure the magnetic moment of the proton. This was refined, of course, by using a resonance technique by Isidore Rabi. Isidore Rabi, of course, was a great scientist who was a pioneer in the Columbia physics department. He had, I think, the largest number of Nobel laureates, his students who became Nobel laureates. And that list is given here. Schwinger, Ramsay, Murray-Gell-Mann, Leon Lederman, Leon Cooper got the prize for the BCS theory for superconductors. Martin Pearl for the discovery of tau. Murray-Gell-Mann, of course, well known for his quark theory, but also for QCD. Norman Ramsay for his, I will come to that later slide, for his pioneering work, both for method that he employed, but also then that became useful in putting tighter and tighter bounds on a possible electric dipole moment. And Julian Schwinger, of course, for his contribution to theory of quantum electrodynamics, prize for which he shared with Feynman and Tomonaga. Okay, so Rabi was, of course, a great figure in those days. He contributed to the founding of the Brookhaven National Lab in 47, to CERN in 1952, to the Nevis Lab in Columbia. Of course, he was an advisor for many, many years, the Atomic Energy Commission in the US. During the war, of course, he worked at the so-called RAD Lab, Radiation Laboratory in MIT, which did a lot of radar research in which many, many bright people were involved, including Luis Alvarez, who later won the Nobel Prize for his work on resonances and so on, using the bubble chamber. Okay, the nuclear shell model got recognized in 1963. Maria Goeppert-Mayer and Hans Jensen for their discovery concerning nuclear shell structures. Just as you have shell structure in atoms, they found evidence for shell structure in nuclei, which is all now textbook stuff. So these are the key articles here. But the prize was shared between them. They got half the prize, and between Eugene Wigner, who was a real giant by way of his contributions to the theory of atomic nucleus and discovering the symmetries therein, both in atoms and molecules, but also in nuclei and elementary particles. And he actually got half the prize. And the other half was shared by Maria Goeppert-Mayer and Jensen. So a few things about Wigner. Wigner, of course, demonstrated the importance of symmetries in both classifying states and so on. He's also, along with Bright, he worked on the theory of nuclear resonances. So you have the Bright-Wigner resonance shape, for instance. And also he worked on the statistical properties. There's a statement, I think I'll not have time to go through this statement, but those of you who are willing could go through the slides later, on comment on the fact that mathematics is unreasonably effective in the field of physics. Okay, so this is something again that I will gloss over, but this the so-called spherical shell model was then worked on to say that nuclei need not be spherical. All nuclei need not be spherical, and in fact, you can have a deformed mean field. And so this for this work, Rainwater, Bohr, and Mottelson got the Nobel Prize. And this was, this was pointed to by several evidences that were there. For instance, in between two closed shells, you found that there were large quadrupole moments, electric quadrupole moments, and they had rotational-like spectra, and so on. So for this, Rainwater, Ben Mottelson, Bohr. Bohr, by the way, was the son of Niels Bohr. They shared the Nobel Prize in 1975. This was the last prize in nuclear physics per se. Okay? There is no prize in nuclear physics as such since that year. People have been nominated for the discovery of radioactive, very strange properties in nuclei, which are very much off the stability line and so on, but they haven't yet got the Nobel Prize. Okay, then I come to this testing symmetry. The nucleus is actually a laboratory for testing many symmetries in nature, interactions and so on, and several are listed here. I will only concentrate on one of them, namely parity. Parity and also time reversal invariance. So parity is a very good symmetry in atoms and also in nuclei till it was found that weak interactions violate parity conservation and violate it actually maximally. And for this, the Nobel Prize was awarded to a pair of young Chinese scientists working then at Princeton, Yang and Li. And they were actually, they actually looked at this problem at following a statement by Feynman, who in one of the particle physics, the so-called Rochester series of particle physics conferences, I think in a summary talk or something, made a statement that my colleague, whom I'm sharing a room with in the conference, he pointed out that is there really evidence that parity is conserved in weak interactions? And initially I was dismissive of this, but then I considered this problem, and then I find that really there is no evidence for parity conservation in weak interactions. And this was, I mean, in the audience were Yang and Lee, and this actually made them look at this question more deeply. And they indeed found that, yes, there is no evidence for parity conservation in weak interactions. And they got, as I said, the Nobel Prize in '57. But the evidence for that was actually found by at least 3 groups. But Wu's was the most direct and simple, not simple, I should say, most direct experiment that showed that parity is violated in beta decay. And she basically looked for the asymmetry of the beta particles that come out of a polarized nucleus. In this case, she looked at cobalt-60. She had to choose the right environment. They had to go down to extremely low temperatures, millikelvin temperatures, in fact. And this was a fantastic experiment done in 1957. A heroic experiment, really, one should say. But the sample was cooled to 3 millikelvin. NIST was the only place which had the expertise to do that. So she interacted with them to get this done. And finally, this is actually there now in textbooks, that this beta asymmetry can be measured. So by flipping the field to change this asymmetry, and then when the temperature goes to higher temperatures, to Kelvin, then of course this asymmetry vanishes. So she was actually in line for the Nobel Prize, but unfortunately there were 2 other groups, the group of Lederman, who looked at such an asymmetry in the muon decay, and a similar asymmetry found by Telegdi in Chicago. So, I mean, it was not possible to give the Nobel Prize to 5 physicists. Of course, these 3 physicists could have been honored later, but somehow this didn't happen, and she missed out on the Nobel Prize. Really outstanding work, and because this led to physicists later on questioning every symmetry. I mean, however good a symmetry looks like to a theorist, is it obeyed in nature? That's the question that people started asking. And now I come to the next part, which is the time reversal invariance in nuclei. So this was something that Ramsay did right from the first experiments, and the electric dipole moment is identically 0 if parity is conserved, but also time reversal invariance has to be violated. And this is actually a goal that he was addressing, that he was looking for. Is there time reversal invariance in nuclei? And if this is violated, then you can, if you find a finite electric dipole moment of the neutron, neutral hydron, then you would have evidence for not just parity violation, something which was proposed by them in 1950, but also time reversal invariance violation. Okay, so I will not go to the way he did it, but the Nobel Prize which he got for the invention of the separated oscillatory field methods, that means you make the neutron pass through 2 zones in which you have oscillatory fields, and then they come back and interfere. And in one of the zones, you can put an electric field. So in addition to the precession of the magnetic moment about a magnetic field, you also have a precession, additional small precession due to the precession of the electric dipole moment in the electric field. And then you make them interfere, and you look for small shifts in the interference curves, especially where the slope is the maximum. And this technique was used very effectively to push down the limits from about 10 to the power of minus 20 or so in the early days, minus 19, minus 20, down to about 10 to the minus 26 electron centimeters. We still haven't found a finite electric dipole moment, but this has thrown many of the theories in the dustbin, which said that no, this should be observed at some level or the other. And so this has helped in ruling out, but perhaps one day his technique will be taken to its logical conclusion, and that we will really find evidence for time reversal for a violation of time reversal invariance in nuclei. Okay, then we come to another very important topic of how nuclei are synthesized in the cosmos. So, of course, we now know that the Big Bang took place about 14 billion years ago, and that very soon after the Big Bang took place, some of the earliest elements were formed, but light elements, deuterium, helium-3, and lithium, and so on, but not much else. And Gamow had a theory that all the elements actually came from the Big Bang, but very quickly this was not shown to be correct. Gamow had many, many brilliant ideas, and in fact, the Big Bang was his proposal. So it turned out that nuclei are actually synthesized in stars. So Hans Bethe, who was actually, he was known to be the master of nuclear physics for due to his two seminal articles in Reviews of Modern Physics in the mid-30s, 37, 38. So he took upon himself to find out if nuclear physics can say anything about the synthesis of elements in stars. And indeed, he first proposed CNO as the cycle contributing to that, but then later found that no, the PP chain is equally important. And for these contributions, which were later borne out by experiments, he got the Nobel Prize in 1967. In 1983, William Fowler got the Nobel Prize for his theoretical work and experimental studies of nuclear reactions. So he had a group in Caltech which measured many of these very fundamental reaction cross sections down to fairly low energies, which helped in understanding the synthesis of chemical elements. Incidentally, in 1983, the other person was the very famous Subramaniam Chandrasekhar. For his theoretical studies, he got it very late. I mean, he should have got it probably 20, 30 years before this 83 that he got it. So he got it for his studies of structure and evolution of stars. Okay, I'll not say too much about this slide, but the key papers are listed here. And the seminal paper in this field is a paper in Reviews of Modern Physics in 1957 due to the two Burbages, husband-wife pair, Margaret Burbage and Jeffrey Burbage, and William Fowler, who also did experiments at Caltech, as I said, and Fred Hoyle. Fred Hoyle had really a key role to play. Okay, I'll just buzz through this slide. The nuclear fusion reactions, the PP cycle reactions are given here. P plus P goes to deuterium, E plus and nu E. So this is a weak interaction, and this is fortunate because since it is weak, the sun can live for billions of years, and indeed life could not have evolved were it not for this weak interaction process. And then there are several reactions that ultimately lead to 4 protons combining to give 2 neutrinos, 2 beta particles, and helium, and release 24 MeV energy in the process. And these 2 neutrinos, of course, are from various processes here, and the spectrum was calculated very meticulously by Bacall and so on. And the evidence for the fact that these fusion reactions take place in the core of the sun was the detection of these neutrinos by Davis and later by many, many other experiments. The SNO experiment in particular solved the so-called solar neutrino problem. Okay, so Hoyle had a very important contribution in this whole business. Apart from all the reactions that go on later, there is a bottleneck at A equal to 8, and Hoyle suggested that there has to be a state in carbon-12 at 7.7 MeV. Otherwise, the proposal earlier were that you make beryllium 8 and then you can combine with a alpha, or that 3 alphas can come together. That was a proposal by Bethe, but all of this was shown not to work unless there is a resonant kind of reaction that takes place. And so he basically told the nuclear experimentalists to go and look for this state in carbon-12. There has to be a state in 7.7 MeV if we have to cross this A equal to 8 barrier. And indeed, based on a private communication, this was found in 1953 by Dunbar and company. This is the 7.6 MeV excitation. This was done through the nitrogen-14 D-alpha reaction using a spectrometer. And later on, of course, this state came to be known as the Hoyle state. So the 1983 Nobel Prize, actually there is a notable omission in that Hoyle should also have shared this Nobel Prize. And in fact, Fowler is reported to have phoned up Hoyle saying that, did you get a phone call from Stockholm? He said, no. So anyway, then they realized that only Fowler had got the Nobel Prize, and Hoyle, of course, very congratulated Fowler. But this was an omission on the part of the Nobel Committee. probably one of the reasons was that Fred Hoyle was an outspoken person, and in some places he had already criticized the Nobel Committee, and maybe that was the reason why he was not given the Nobel Prize. He was sort of considered to be an anti-establishment person. Okay, how can heavier elements be made? Okay, this can happen in situations where you have neutron capture, and this was very well spelled out in the that paper that I showed, the V squared FH paper, that you can have neutron captures, you can go to heavier nuclei, and finally this has to compete with beta decay. So if beta decay takes over, then of course you go to 1Z higher, and this keeps on happening till you reach a point where the beta decay process is very slow and it can capture a neutron. But you require very large neutron numbers, and that can happen when you have supernova explosions, where the numbers can go beyond 10 to the power of 50 and so on. And in fact, these neutrinos were also observed in the process where you produce neutrons and neutrinos. So you can have electron captures by proton to produce a neutrino and a neutron, and then these neutrons can get captured and produce all the heavier elements. However, the calculation that we now have seem to suggest that the production of these heavy elements in supernova is really not enough to account for all the abundances that we see. And indeed, neutron star mergers are probably contributing equally to this process of making heavy elements. And we saw the first evidence of a neutron star merger through the gravitational wave signals that we saw. And indeed, which started the so-called multi-messenger astronomy, namely that the gravitational waves, I mean, when you see them, you also see X-rays and visible light and radio waves. This, of course, doesn't happen in black hole mergers, but it does happen in neutron star mergers, and probably will happen in neutron star black hole mergers as well. Okay, Macmillan and Seaborg produced a whole series of elements, transuranic elements, for which both of them got the chemistry Nobel Prize in '51, and this was fairly pioneering work. So they produced, I think, one whole line of elements in the periodic table, and these are the references. I think I will have to speed up in view of the time. This led, of course, to the prediction later of a super heavy island of stability, so-called SHE, super heavy element island. And we have probably just touched on the parts which are neutron deficient in this island. This has also led to the so-called radioactive ion beam efforts in the world, where we want to produce elements way beyond these stable elements that we have, but also the very neutron-rich elements. So we now know that there are about experimental evidence for 3,000 elements, 3,000 nuclei, but there are expected to be something between 7,500 and 9,000 elements that exist from calculations that we have of their masses and so on, stabilities. So people are working towards these super heavy elements. As I said, we have already produced less neutron-rich heavy elements. The heaviest element that has been produced is 294, A equal to 294, Z equal to 118, and only 3 events in a 25-day run at a Russian accelerator. This is the modern IUPAC periodic table. I think a couple of years back, we had the 150 years of the periodic table of Mendeleev. And you can see that the elements here, they have all been produced by accelerators. So the heaviest element, 118, is named after a pioneering scientist from Russia, Oganesyan, and it's called Oganesyan, something like that. So it is an element which is named after a living scientist who has contributed greatly to our synthesizing very heavy elements. And there's a whole series of these elements which have been produced in Berkeley, in GSI in Germany, and in Dubna in Russia, in the old USSR. Okay, finally, just one slide on particle detectors and applications. CTR Wilson, of course, got the Nobel in '23 for his cloud chamber discovery, where you could actually visualize charged particles. Blackett for the development of this Wilson cloud chamber, for using it in fields such as nuclear physics and cosmic radiation. He contributed to cosmic ray physics as well. Donald Glaser got a Nobel Prize in 1960 for inventing the bubble chamber, which was used very effectively by Luis Alvarez and many others. Luis Alvarez, in fact, got the Nobel Prize for discovering many resonances and so on in Berkeley, using the improved version of the bubble chamber. Georges Charpak at CERN for his invention of the multi-wire proportional counter and many other detectors that he developed when he was at CERN. George Heafsey, there is, I think, some problem with this way this slide was made. Okay, George Heafsey for his use of isotopes, in particular radioactive isotopes as tracers, to map out chemical processes. This was in 1943, the Chemistry Nobel Prize. Libby for his technique of using carbon-14 to date objects in archaeology, geology, geophysics, and so on. So these are the applications. And I think this is my last slide. So thank you all for the attention. So I hope I've communicated, the sense of how nuclear science developed and how it is still being used in various areas of science. Thank you.
Thank you very much, sir.
I'll be happy to take questions if any.
Now, let me invite Dr. Narasimha Raju to moderate the question and answer session.
Thank you, Sridevi. Good evening to everyone. I would like to thank the distinguished speaker, Professor V.M.Datar, for his nice presentation. And I'd like to thank the organizing committee for giving this opportunity to chair this question answer session. Now, the session is open for question answers. And we have 10 minutes time for the question answer session.
Are there any in the Zoom chat or something? I can't see the chat right now. But maybe I can, if I stop sharing, perhaps I'll be able to see that, right? Maybe I can stop share. Yeah. So are there any questions in the chat? No, not yet.
There is a question in the YouTube stream which I will read out.
Okay. Are there any in the Zoom chat or something? I can't see the chat right now.
No, sir, not yet.
No, there are no questions in the Zoom chat, but YouTube there is one question. I'll read it out. Am I audible?
Yes, sir.
Yes, I can hear you.
So the question is, would the Nobel Prize in the field of neutrinos help in the progress of the India-based neutron observatory?
Well, not directly, but yes, we have requested, and the Nobel laureates had indeed very kindly obliged. The 2015 Nobel Prize was awarded for the discovery of neutrino oscillations to two scientists, one from the Sudbury Neutrino Observatory, Professor Art McDonald, and to Professor Kajita from the Cosmic Ray Laboratory in Japan. And they were very kind enough to give their statements in support of the INO project. In fact, I remember Art McDonald also had a program when he came to India. Of course, he gave several lectures, but I remember also an interview of his on NDTV where he said that this is an important. Of course, he described the SNO project and the discovery that that led to the solving of the solar neutrino problem. But he also, at the end, highlighted the INO and said that this is a very good project. And so, yes, some of the Nobel laureates have indeed said good things about the project. But of course, the project movement also has to do with lots of other social issues and so on. So we are actually right now combating the social issues, socio-political and so on. So we hope that we will see the end of the tunnel perhaps after the elections in Tamil Nadu.
Thank you, sir. So we have one more question in the chat box. Shall I read the question?
Yes, sure.
Kindly comment on methods of detecting violation of time reversal symmetry in particles. That's the first question.
Yeah. Okay. So for looking at violation of any symmetry, you have to find out an observable which will lead you to discovering a violation. For instance, in the case of parity, the observable that was looked at by, for instance, Madame Wu was a dot product of the spin of the of the nucleus and the momentum of the electron, the decay electron. And if parity is obeyed, then this should have been identically zero. But she saw an asymmetry, not just saw a small asymmetry, but a maximal asymmetry. So that's how the conclusion was that parity is violated maximally. So similarly, in the case of T reversal invariance, you have to look at an observable which is, let's say, odd in T, but let's say even in parity, for instance. It could also be odd in parity, but certainly it has to be odd in T. And if you consider the observable of the electric dipole moment of the neutron is an electrically neutral object. So the only vector that you have is the spin of the neutron, and the spin is like a r cross p, so it's a time reversal odd observable, right? If you change time to t to minus t, then p goes to minus p, whereas r doesn't change. So the electric dipole moment is proportional to this spin, because that's the only vector that you have to play with. And therefore, if time reversal invariance is obeyed, then this observable should be zero. So the electric dipole moment should be zero. So any evidence of finite electric dipole moment of the neutron would immediately imply that time reversal invariance is violated. That's why it's a very important experiment. And in fact, worldwide, they are now trying to push this limit to about 100 times the upper bound that Ramsay had in his lifetime. Because Ramsay is no more, but his methods have been refined and refined. And someday, hopefully, we will observe the electric dipole moment of the neutron.
Thank you, sir.
Yeah, so this is an answer
question
to the first question. The second question, okay, I can also read out. Who is the Nobel Committee? Okay, so the Nobel Committee, it should not be BLE, it should be BEL, is the Nobel Committee. That consists of some eminent people in Stockholm, in the, I think, the Royal Institute of Physics or some such body. So they have eminent people. I don't know how, if I remember right, it's a group of about half a dozen people, and they get nominations from earlier Nobel Prize winners, but also eminent people in the field, and then they whittle it down to a few, and then they discuss this threadbare that who should be awarded the Nobel Prize, and it's all kept secret. In fact, you don't know who was nominated and who didn't make it to the Nobel Prizes for, I think, a period of something like 75 years. So this data on Meitner and so on is only because 75 years have passed, and then now we have access to that. So whatever happens today in the Nobel Committee, you will not know for the next 75 years. Okay, so it's basically the decision of the Nobel Committee, which of course consists of very eminent scientists in their own right. Yes.
I have a question.
Yes.
So, in your, probably many years of service in the nuclear science field, do you think that there was any discovery in India which deserved a Nobel Prize but was unnoticed by the?
Well, okay. There was perhaps one discovery of spontaneous fission that was made, and unfortunately, I don't know. I don't know how it happened, but spontaneous fission was discovered by an Indian scientist, I think, in the Bose Institute. However, that the paper that was sent out to a journal was asked to be retracted by the then director of that institute. That is the story that I've heard. I have not myself verified the veracity of it, but this has appeared in some literature that this was asked to be retracted. And later, I think 1 year later or 2 years later, Flerov got recognized for that, the discovery of spontaneous fission. I think he got the Nobel Prize, but I'm again not too sure of that. But that discovery certainly would have deserved the Nobel Prize, because spontaneous fission is something that is sort of counterintuitive for those times. I think this happened in the mid 50s or something, or the late 40s. That was one. The other was that there was I think, I don't know whether it was Abha Chaudhary or whether it was somebody else, a lady scientist, I think, who was involved. Was it a lady? I don't forget. They almost discovered the pion, but the quality of the plates that they had did not quite, convince other people. I think it was Ilford plates. And this was, I think, before India became independent. So they did this search in, I think, Darjeeling or somewhere. They found evidence for a particle that was decaying, and which later turned out to be the pion. But the evidence was not to the minds of, the referees or the people in the Nobel Committee strong enough for them to give this. But it was, a discovery which was in the same class. And Powell had access to, of course, the latest Ilford photographic emulsions, so with a higher resolution. So he could, very conclusively say that, yes, there was a particle which corresponds to having a mass of about 140 MeV or so. And he and Occhieleni made this, had this paper. But they, by the way, referred to the earlier work of the Indian scientists. But the Nobel Committee probably didn't think that that was strong enough evidence for them to include a person from there for the Nobel Prize. But I would say that that was in the same class. They maybe in today, maybe they, if such a discovery were made, they might have even got the Nobel Prize, possibly. So these are two things that I know of. I don't know of any other, but that's not to say that there aren't any such cases. But at least these two cases I have heard of.
Thank you, sir. There's one more question in the chat box.
But by the way, there's no reason why some of our young folks cannot make a discovery in the future and, get a Nobel Prize in this area of nuclear science, nuclear and particle science.
Do you have ideas on which topics would be interesting that would bag a Nobel Prize in the coming years to come?
That's a difficult question to ask, because it also. But some of these discoveries are serendipitous discoveries. If you're working in a frontline area, you discover something that was completely unexpected. So that is what I think might happen to ICAL detector when it is built in the INO laboratory. But there are several areas where you suppose you discover a magnetic monopole using ICAL. That's a Nobel Prize winning discovery, because many people have searched for it and not found evidence for it. If you discover neutrino-less double beta decay, of course, that will be hard, because there are many groups, about a dozen groups working on it worldwide. But who knows? If we discover something like that, or evidence for dark matter, or something which we even cannot think of right now. So if you build a state-of-art detector, there is a very strong possibility that you might find something which you didn't expect. Let me give you two examples of this. I hope there is time. Deepak, can I give these two examples, or if there's no time, then we can stop here?
No problem. No problem.
Okay. So, for instance, the Kamioka 50 kiloton detector, actually the earlier 3 kiloton version as well, but the 50 kiloton version really settled the issue, was actually built to find evidence for proton decay. Okay. KGF was the first experiment to get going, and they put interesting bounds. If protons had decayed at the rate that Pati and Salam had predicted, Indians would have got the Nobel Prize, okay, for making the first experiment that found evidence for proton decay. But that was not to be. Protons are still, found to be stable, at least to the limit that we have. And the Kamioka did not find evidence for proton decay, but the background in that experiment was neutrinos. And they made the seminal discovery of neutrino oscillations. Atmospheric neutrinos were used to show that there are oscillations. They found an up-down asymmetry in the muon neutrino to electron neutrino ratio. And this was absolutely independent of the dynamics how they are produced and so on. Is a very robust way of saying that the up to down ratio is different from what you expect, and so it doesn't depend on an absolute number, how many atmospheric neutrinos are there, but just depends on the ratio, which throws out most of the uncertainties in the calculation. So this was a byproduct. This was something that was not intended to be when the detector was first built. Neutrinos were a background, but that background turned out to be a signal and a source of discovery of neutrino oscillation. One example. Second example is CP violation. So the electron-positron collider at KEK was actually built to discover the top quark. So you look at the electron-positron collisions and then look at the hadrons that are produced. And this ratio, electron going to hadrons to muons, that ratio shows jumps when you start producing heavier and heavier quarks. So they expected that you will see a step due to top quarks. But it turned out that the top quark was too heavy to be discovered at KK, which was could only produce center of mass energies up to, I think, about 30 GeV. But they didn't discover top quarks. But nevertheless, that machine became very useful for producing asymmetric E plus E minus collisions and leading to proving the theories of Japanese theorists who had a theory for CP violation, and that there are 3 generations of quarks and so on, that they are necessary for CP violation. So in BB bar production, this was used, and the theory that was written down by 2 Japanese theorists was actually fleshed out by experiments done at KEK with asymmetric E plus E minus beam. So the accelerator had to be modified to do that, but this led to our deep understanding of CP violation in the B sector, and that fetched 2 Japanese scientists the Nobel Prize for that. So these are at least 2 examples of instances where you build something to to understand physics in a certain sector, but you don't discover that which you had aimed for, and instead you discover something completely different in a different area. I hope that at least partially answers your question, Deepak.
Yeah, thanks. Thank you.
Yeah.
Right, the moderator seems to be offline, I think. Anyway, there's one more question in the chat box.
Okay.
It's on, I'll read the question. It's on the chat box.
Is there in chat box? Okay. Is this the question from Pooja? On what basis the Nobel Prize is awarded? One point was considered that the discovery or invention is fruitful to mankind. Apart from this, what else is taken across? No, I mean, this is one of the possibilities that it's useful to mankind. But if it solves a problem, a very fundamental problem, or it improves greatly our understanding of certain phenomena, then the Nobel Committee can consider that individual or set of individuals for the Nobel Prize. So, for instance, the discovery of parity violation, of course, the experimental part was done by a different set of people, but the proposal that you look for it was done by Li and Yang. And as far as we know, this hasn't led to any practical use. But of course, that doesn't rule out the possibility that they may be useful sometime, except for the fact that weak interactions are extremely, necessary for instance, the sun to shine. But parity somehow doesn't enter into that. But in any case, that is an integral part of weak interactions, that parity is violated maximally. But for instance, it could lead us to understand why molecules have a certain handedness. The origin could be in the violation of parity in weak interactions. We haven't shown that yet, but it could be that these two phenomena are related. The sugar that you have in your body has a certain handedness. You don't have sugar of the other type. Proteins, they have handedness. And why is that so? This question has been bothering people for a long, long time. In fact, the solution to that would, I think, also lead to a Nobel Prize. And it could be that weak interactions are indeed responsible for this left-right asymmetry.
Thank you, sir. I'm sorry. I think Dr. Nasimraju is.
There is one question here which says slide containing the periodic table whether the element with Z equal to 109 was circled. Any specific reason to that? I'll have to find out. Let me see if I can look at this slide in question. Slide number 39. This was just to show that although Lise Meitner didn't get the Nobel Prize, she was honored via the element that was named after her, called Meitnerium. Okay, can you hear me? Sorry. Hello.
Yes, yes, we can.
Yeah. Okay. So I just had circled it because I mean, she should have shared the Nobel Prize with Hahn for the discovery of fission, because she was the one who started the program and who interpreted the results of Hahn. Hahn was a chemist, so he was really puzzled by this. How come these two elements are there? She told her to go back, told him to go back and do the chemistry again carefully in some way, through a letter. He did that. He is an extremely competent chemist. He's a great chemist. So he reported the same results. And then she said, okay, then she proposed that, the nucleus breaks up. And so, as I said, she should have shared the Nobel Prize, but somehow the Nobel Committee did not share this view. And but anyway, she got some of the highest awards in the US. I think the President's Medal and so on, the Enrico Fermi Award, and of course an element was named after her called meitnerium. She, as I said, I think you remember that she discovered the element protactinium.
Thank you, sir.
Yeah.
So no questions in chat box.
Dr. Raju, there is one question in YouTube. Shall I ask?
Okay. Sure, sir. Please.
Professor Datta, there's one question from
Sure.
Chowdhury.
Yeah.
Will India strive for building its own particle accelerator in near future, like in CERN, for the research and development in the field of nuclear and particle physics?
Okay, so there is a plan to, I think in a shorter term, to build a spallation neutron source. So this will be a high current 1 GeV proton accelerator. It will of course produce pions and muons and so on, and they will be very useful for condensed matter. For instance, muons are used as probes of very small magnetic fields and so on in condensed matter systems. Pions are used for also various studies involving secondary beams of pions are used in nuclear physics, for instance. They can also be used, for instance, to study the response of detectors and so on. Another spin-off of this, a similar facility which is working very well in the US, is the so-called Oak Ridge spallation source. And that has produced the first evidence for coherent neutrino scattering. That was some prediction that was made in 1974. And I think the experiment that produced the first evidence was, I think, in 2017 or thereabouts, 2017, 2018. So it was almost 45 years or so after the prediction that was done by a Fermi-Lab theorist to actually measure this. And this was done at a neutron spallation source. Okay, so nobody would have imagined maybe 20 years ago that a spallation neutron source, which was supposed to, complement nuclear reactors as sources of neutrons for doing condensed matter research, that it could also do fundamental, particle physics, indeed neutrino physics. And these coherent neutrino sources, for instance, because of the coherence of the interaction, has led to the possibility of making neutrino detectors, which are about 100 times smaller than the huge neutrino detectors that we have today. Of course, they are not as versatile as these detectors, but they have a niche area, and in a niche area they can be 100 times smaller than the huge neutrino detectors. So this discovery of coherent neutrino scattering, as I said, was done. So India has this program of making the spallation neutron source, but also that will later probably be the stepping stone to the so-called ADS machine, the accelerator-driven driven systems to produce energy. So if you have 5 to 10 milliamperes of 1 GeV protons, you can actually make a large number of neutrons, and so the assembly can be subcritical, but can produce about 5 times the energy that you needed to actually accelerate that proton to 1 GeV of that high current. So this is another program that we have, but I do not think there is any proposal, because that has to come from the particle physics community. The particle physics community has not proposed any accelerator of this sort. But as I said, secondary beams from some of these facilities could be used for fundamental experiments. Spallation neutron sources are also used, by the way, for looking at neutron electric dipole moments. That's a fundamental physics problem, right? So even I think in Switzerland there's a machine of which produces 500 and high currents, I think 3 milliampere or something, of 500 600 MeV protons, and that is a source of these neutrons, which are then thermalized and indeed cooled down to very low temperatures and then used for neutron electric dipole moment measurements.
Thank you, sir.
Thank you, sir.
Yeah.
We are moving into our last part of today's session. It is my privilege to invite Dr. Rajesh Joshi, Assistant Professor of Physics, Central University of Karnataka, to propose the vote of thanks.
Thank you, Sridevi, for this opportunity. At the outset, I thank Professor V.M.Datar for this tingling talk to our young minds. I believe every inspiration and the historical account of the scientific ventures motivates minds to get into science as well as do science very seriously. May it be the history of Curie couple, which really remained accommodated. May it be Professor Meitner's tale of her contribution with Professor Hahn, or it could be the Enrico Fermi's tale, where he has pioneered his life in theoretical physics as well as experimental physics. The institutionalization capacity of Professor Rabi, who developed scientific institutions for promoting science, or it is Young and Lee, who actually sat in Feynman's lecture and listened very carefully and learned beyond lines and time and could develop an idea which is Nobel worthy. Or may it be the story of Ramsay, who actually innovated to such a level that time became his slave. So that's quite interesting to realize. These all tingling stories have inspired our young minds. Thank you, Professor Datar, for this wonderful talk. And we are listening to you after something like around 11 years, I believe. I was at BARC listening to you in a corner of the auditorium. Thank you again, seeing you here and inspiring all our children. Thanks indeed, sir. And now it's my duty to thank Indian Physics Association, both for Research in Nuclear Sciences, for their support in organizing this talk. Professor Vandana for being the backbone behind this activity, being the host for this program. Mr. Ravindra Shinde, who has been a technical support to this activity and making the talk possible be on YouTube and reach across the world. Thanks to all of you for making this activity possible. I'll fail in my duties if I don't thank Professor M.V. Alagwadi, our Honorable Vice Chancellor, who is always a support to the scientific ventures at CUK and a very inspiring person himself, a man of commitment. Thank you, sir, for being with us for this activity. Professor Donur, always a support of the academic activities at the campus. Thank you, Professor Donur, for supporting this whole venture. It's Mr. Vinod and Mr. Manjunath who have made it possible to be on Zoom at the CUK side, and they were being technical support to us to host this activity. Thank you for this whole support. I will be failing in my duties if I don't mention contributions of Dean, School of Physical Sciences, Dr. Deepak, who is the initiator of this activity. Thank you, Deepak, for bringing this wonderful talk to all our children. Dr. Bharat, Dr. Suchismita, and Dr. Narasimharaju, and all our faculties at the Department of Physics who have contributed and joined their hands to make this activity a success. I would be failing in my duties if I don't thank all my fellow friends, all the student community of Department of Physics, Central University of Karnataka, and the science enthusiasts who have listened to this tingling talk. Thanks to all of you. This has been a wonderful journey going across the venture of discoveries which have led to Nobel Prizes in nuclear sciences. Thank you. Thank you all. Thank you
very
Shruti,
much,
for this opportunity.
Dr. Joshi.
Thank you, sir. May I request all you to unmute and switch on the camera and clap your hands to thank our speaker.
Okay. Thank you. Thank you very much.
Thank you, sir.
Thank you all. I would like to extend my warm regards and gratitude to all on behalf of the School of Physical Science for making this session a fascinating one. We are now closing the session and we appreciate everyone for joining us today. Thanks and goodbye.
Thank you.